We live on a planet that takes a leisurely 24 hours to complete a single rotation. At the equator, Earth spins at a modest 460 meters per second, enough to give us day and night, but slow enough that we never feel the momentum. Deep in the Sagittarius constellation, there is a dead, city-sized star that completes a full rotation 716 times every second. This is PSR J1748 2446 AD, a millisecond radio pulsar, and the current natural record holder for rotational speed. To put that frequency into perspective, the surface of this 30-kilometer wide sphere is whipping through space at 72,000 kilometers per second. That is roughly 24% of the speed of light. It didn't start out this fast. Over billions of years, this pulsar has been siphoning gas from its companion star, a small, dim red dwarf. As that material spirals inward, it acts like a cosmic accelerator, continuously pushing the neutron star to its blistering speed. What makes this speed so intriguing is a recent discovery involving a completely different stellar object. Astronomers measured the spin of an X-ray binary called 4U 182030, powered by violent thermonuclear explosions on its surface. Its rotation speed clocks in at exactly 716 Hz. These two systems share almost nothing else in common. While the radio pulsar takes over a day to orbit its red dwarf, 4U 182030 is locked in an ultra-compact 11-minute sprint around a dead white dwarf. Two radically different dead stars with completely different evolutionary paths, peaking at the exact same frequency. This identical match points to a hard ceiling in astrophysics, a universal speed limit for dense matter. If an Earth-sized planet tried to spin 700 times a second, it would instantly fly apart. These neutron stars only survive because their material is so thoroughly compressed that a single teaspoon weighs 1 billion tons. Every rotating body fights a tug of war. Gravity pulls inward, while centrifugal force rips outward. Approaching 1200 Hz, a breaking point called the cosmic governor, centrifugal force wins. The star either bleeds energy through gravitational waves, or its crust shatters into the vacuum. Both of our record holders top out at 716 Hz, because they are hovering right at the edge of this red line. It is the absolute peak safe operational zone, before the laws of mechanics violently dismantle them. There is one class of star that achieves extreme speeds without a companion, but only briefly. In early 2026, astronomers observed the birth of a magnetar, a highly magnetic neutron star, spinning every 4.2 milliseconds, or roughly 238 times a second. While our 716 Hz champions will maintain their speed for billions of years, this newborn magnetar's velocity is a temporary condition of its violent birth in a supernova. Its defining feature is its break. Possessing a magnetic field 400 trillion times stronger than Earth's, these intense lines drag against space itself. This friction bleeds rotational energy into the void, slowing it to a lethargic multi-second rotation within millennia. To maintain a record-breaking spin, an object must be relatively devoid of intense magnetism. The universe requires you to trade magnetic power for pure, sustained velocity. But limits like gravity, centrifugal force, and magnetic friction all rely on an object having a solid physical surface. What happens to the speed limit when you remove the surface entirely? You get a singularity. Objects like the supermassive black hole GRS 1915+105 ignore the structural rules of solid matter. Because a black hole is a region of collapsed space, its event horizon can rotate at nearly the speed of light. It spins so fast that it exhibits a relativistic effect called frame dragging, physically twisting the fabric of spacetime along with its rotation. Ironically, to find anything spinning faster, we have to look down rather than up. Using lasers called optical tweezers, researchers have levitated microscopic silica nanoparticles in a vacuum, spinning them to 5 billion Hz. Yet, the hunt for the ultimate natural spinner continues. Astronomers are actively searching the sky for a sub-millisecond pulsar, a physical star completing over 1,000 rotations per second. Discovering an object that dense, moving that fast, would immediately invalidate the cosmic governor theory, forcing physicists to rewrite the equations that govern dense matter and nuclear physics. Until our telescopes find a star that breaks the math,
716 Hz remains the peak. It is nature's ultimate physical limit for solid matter, holding the fastest objects in